According to the 2002 National Electrical Code, specifically Article 240.85a, there are restrictions on using a 120/240 volt 2-pole circuit breaker on a high-leg delta system to supply a 120/240 volt 3-wire single-phase load. The core issue revolves around the potential for overvoltage if the breaker were inadvertently placed in the high leg, also known as the stinger leg or B phase in some installations. A high-leg delta system is a three-phase electrical service where one phase, typically the B phase, has a higher voltage to ground than the other two phases. In a standard 120/240 volt high-leg delta system, two of the phases, A phase and C phase, will have 120 volts to ground, while the high-leg B phase will have approximately 208 volts to ground. This 208 volts to ground is what makes it crucial to avoid placing any 120 volt rated components on that phase. Now let's delve deeper into the reasons why this restriction exists. Circuit breakers are designed with specific voltage ratings, indicating the maximum voltage they can safely interrupt. A 120/240 volt breaker is designed to interrupt circuits with voltages up to 240 volts between phases and 120 volts to ground. If a 120/240 volt breaker is connected to the high leg, which has 208 volts to ground, it exceeds the breaker's design voltage rating to ground. This can lead to several problems. Firstly, the breaker's insulation may break down over time due to the higher voltage stress. This can result in a short circuit within the breaker itself, potentially causing a fire or other hazardous conditions. Secondly, if the breaker attempts to interrupt a fault in the high leg, it may not be able to do so effectively because it's not rated for that voltage level. This can lead to arcing, prolonged fault current, and damage to the electrical system. Article 240.85 is in place to prevent these scenarios and ensure the safety of electrical installations. It mandates that breakers used on high-leg delta systems must be specifically rated for the voltage to ground of the high leg. This typically means using a breaker rated for 240 volts, even if it's only being used to supply a 120 volt load on one of the other phases. This ensures that the breaker can safely handle the voltage to ground on any phase of the system. Now let's consider the practical implications of this code requirement. When installing a 120/240 volt breaker in a high-leg delta panel, it's essential to identify the high leg. This is usually done through color coding, with the high leg typically marked with orange tape or paint. Once the high leg is identified, ensure that the breaker is not placed in a position where it could be connected to that phase. This might involve skipping a space in the panel or using a breaker lockout device to prevent accidental installation in the wrong location. Furthermore, it is essential to carefully verify the voltage to ground of each phase before connecting any equipment. This can be done using a voltmeter to measure the voltage between each phase and ground. If the voltage to ground in the high leg is significantly higher than 120 volts, it's a clear indication that you're working with a high leg delta system and that the code requirements of Article 240.85 must be followed. It is also important to note that the specific requirements for breaker ratings and installation on high-leg delta systems may vary depending on the local electrical codes and regulations. It's always best to consult with a qualified electrician or electrical inspector to ensure that your installation complies with all applicable requirements. In summary, Article 240.85 of the 2002 National Electrical Code prohibits the use of a standard 120/240 volt 2-pole circuit breaker on a high-leg delta system to supply a 120/240 volt 3-wire single-phase load. This restriction is in place to prevent overvoltage and ensure the safety of the electrical system. When working with high-leg delta systems, it's crucial to identify the high leg, use appropriately rated breakers, and verify the voltage to ground of each phase. By following these guidelines and consulting with qualified professionals, you can ensure a safe and compliant electrical installation. Let's delve further into the specifics of high-leg delta systems and the implications for circuit breaker selection. A high-leg delta system is a type of three-phase electrical service commonly used in commercial and industrial settings. It offers the advantage of providing both three-phase power for motors and other heavy equipment, as well as single-phase power for lighting and receptacles. However, the presence of the high leg, with its higher voltage to ground, introduces certain complexities in terms of electrical safety and code compliance. One of the key challenges is ensuring that all electrical components connected to the system are properly rated for the voltage to ground on each phase. This is particularly important for circuit breakers, which are designed to interrupt fault currents and protect equipment from overloads. As mentioned earlier, a 120/240 volt breaker is designed for use in systems where the voltage to ground does not exceed 120 volts. If this type of breaker is connected to the high leg, where the voltage to ground is typically around 208 volts, it can be subjected to excessive stress and may fail to operate properly in the event of a fault. To address this issue, the National Electrical Code requires that all circuit breakers used on high-leg delta systems be rated for the maximum voltage to ground present in the system. This typically means using a breaker with a voltage rating of at least 240 volts, even if it is only being used to supply a 120-volt load on one of the other phases. By using a breaker with a higher voltage rating, you can ensure that it is able to safely handle the voltage to ground on any phase of the system, including the high leg. In addition to voltage rating, it is also important to consider the interrupting capacity of the circuit breaker. The interrupting capacity is the maximum amount of fault current that the breaker can safely interrupt without being damaged. In high-leg delta systems, the potential fault current can be higher than in other types of electrical systems due to the presence of the higher leg. Therefore, it is important to select a circuit breaker with an interrupting capacity that is sufficient to handle the potential fault current at the installation location. The interrupting capacity of a circuit breaker is typically marked on the breaker itself in amps. It is important to consult with a qualified electrician or electrical engineer to determine the appropriate interrupting capacity for your specific application. Another important consideration when working with high-leg delta systems is the proper identification and marking of the high leg. The National Electrical Code requires that the high leg be clearly identified with orange tape or paint at all accessible locations, including the service entrance, panel boards, and disconnect switches. This helps to prevent accidental connection of 120-volt equipment to the high leg, which could result in damage or injury. In addition to color coding, it is also important to use appropriate warning labels to alert personnel to the presence of the high leg and the potential hazards associated with it. These labels should be placed in prominent locations and should clearly state the voltage to ground of the high leg. Furthermore, it is essential to provide adequate training to all personnel who may be working on or near high-leg delta systems. This training should cover the specific hazards associated with these systems, as well as the proper procedures for working safely around them. By providing adequate training, you can help to prevent accidents and ensure the safety of your employees. In conclusion, working with high-leg delta systems requires a thorough understanding of the applicable codes and regulations, as well as a commitment to safety. By following the guidelines outlined above, you can help to ensure that your electrical installation is safe, reliable, and compliant with all applicable requirements. Remember to always consult with a qualified electrician or electrical engineer if you have any questions or concerns about working with high-leg delta systems. Now let's talk more about the specifics of Article 240.85a. This section of the National Electrical Code deals specifically with the protection of electrical systems in situations where the available fault current exceeds the interrupting rating of the circuit breakers or fuses. This is a critical aspect of electrical safety, as it helps to prevent catastrophic failures and minimize the risk of injury or property damage. Article 240.85 outlines several methods for protecting electrical systems from overcurrents, including the use of current-limiting devices, series ratings, and other approved methods. Current-limiting devices are designed to rapidly reduce the magnitude of fault currents, thereby protecting downstream equipment from damage. These devices typically consist of fuses or circuit breakers with special characteristics that allow them to interrupt fault currents very quickly. Series ratings involve the use of two or more overcurrent devices in series, with the upstream device providing protection for the downstream device. This allows for the use of lower interrupting rating devices in certain applications, provided that the overall system is properly coordinated. In addition to these specific methods, Article 240.85 also allows for the use of other approved methods for protecting electrical systems from overcurrents. These methods must be carefully evaluated by a qualified electrical engineer to ensure that they provide adequate protection and comply with all applicable codes and regulations. When selecting overcurrent protection devices for high-leg delta systems, it is important to consider the specific characteristics of the system and the potential fault currents that may occur. The available fault current at any point in the system will depend on several factors, including the size of the transformer, the impedance of the conductors, and the presence of any other equipment that may contribute to the fault current. It is essential to perform a thorough fault current study to determine the maximum available fault current at each point in the system. This study should be conducted by a qualified electrical engineer and should take into account all relevant factors. Once the available fault current has been determined, it is possible to select overcurrent protection devices with an interrupting rating that is sufficient to handle the potential fault current. It is important to note that the interrupting rating of the overcurrent protection device must be equal to or greater than the available fault current at the point of installation. If the interrupting rating is less than the available fault current, the overcurrent protection device may fail to interrupt the fault current, which could result in damage to the electrical system or injury to personnel. In addition to selecting overcurrent protection devices with an appropriate interrupting rating, it is also important to ensure that the devices are properly coordinated with each other. Coordination involves selecting overcurrent protection devices with time current characteristics that allow them to selectively trip in the event of a fault. This means that the overcurrent protection device closest to the fault should trip first, while the upstream devices should remain closed. This helps to minimize the extent of the outage and prevent unnecessary interruptions of service. Coordination studies are typically performed by qualified electrical engineers and involve the use of sophisticated software tools to analyze the time current characteristics of the overcurrent protection devices. The results of the coordination study are used to select the appropriate overcurrent protection devices and to adjust their settings to ensure proper coordination. Finally, it is important to ensure that all overcurrent protection devices are properly installed and maintained. This includes verifying that the devices are properly sized, that they are securely mounted, and that they are regularly inspected and tested. Proper installation and maintenance are essential to ensure that the overcurrent protection devices will operate reliably in the event of a fault. In conclusion, Article 240.85 provides important guidance on the protection of electrical systems from overcurrents. By following the guidelines outlined in this article, you can help to ensure that your electrical system is safe, reliable, and compliant with all applicable codes and regulations. Remember to always consult with a qualified electrical engineer if you have any questions or concerns about overcurrent protection.